Alrighty, folks, let's get started. So today I want to talk about testing, but specifically unit testing. So I want to talk about what it is, why you might be interested in it, and how you might go about doing it. Okay. Like a lot of things in this industry, we might not agree. There are a lot of ways to not only test but write software. So to have consensus on how to go about it is likely not even possible. But yeah, if at any point you want to argue or even have questions, just feel free to pipe up and we can get a discussion on the go. Hopefully afterwards we can do questions and have a bit of discussion then as well. Alrighty, so what is testing? It's kind of like checking your math. So as a kid, you were in math class and your teacher would say, you have these solutions or these problems, you need to get solutions for these, and then they would always dock you points for checking your math. So in the real world, quote unquote, nobody docks you points for not checking your math because it's software, and a lot of software goes untested, and I'm sure you all use some version of consumer software that is woefully buggy. Yeah, we're not all writing, the control software for the space shuttle, so it's not life-threatening, but if you don't test your software, likely your users will. So the number one reason, or I guess really what testing comes down to, is software is complex. You can write scripts, they're easy, but as we build things that are worth building, it gets more and more complex. And personally, I'm not going to try and project onto any of you, but I find it extremely difficult to keep even the simplest of programs in my mind, right? So there's cognitive load with trying to understand and reason about software. And the larger a program gets by nature, the more load you have on yourself to keep it in your mind and to be able to trace through, for example, a piece of software. So obviously it gets a lot more complex when you introduce things like teammates. So some of you may work on a team, some of you might have experience in that, and really you can look at it as something that's empathetical to do. So you write code, you might think it's beautiful, perfect little snowflake, but you pass it off to your teammate and they need to make changes to it, and they don't feel comfortable making changes to it because it's either too complex or difficult for them to keep in their mind. So yeah, things that introduce a lot more complexity, teammates, coworkers, users, unfortunately. But I know what you're saying. That sounds fancy, but why? Why do I need to do this? So this is really the part where I push my own agenda. I look at it so a number of ways. There's obviously a lot of ways, like I said, to think about it. You can look at it as being kind to your peers, to your coworkers, as well being kind to future you. The same way we don't write comments and regret it a day afterwards is the same way when we don't write tests. You end up trying to make modifications to the software that you wrote and struggle through that. So, but comfort for me is really another thing that I think is important. Oftentimes people will say, well, that's a small change, right? And in software it might be, but realistically, how comfortable do you feel making that change to your software? So tests give me a way to feel comfortable about making changes, and tests, like I said, give your coworkers and your peers and your teammates, etc., a way to feel comfortable modifying the code that you graciously left them with. Yeah, and it gives you an out, really. If nothing else, you can look at it as giving you an out. When things do break, you can pass off blame and be like, well, why wasn't there a test for that? So, two views that I want to talk about when it comes to why you might want to test your software. Testing improves design, and some say, and again, this is one of those things where a lot of people disagree on, and this is, I guess, as controversial a topic as software is. It's never really that controversial, but this is a controversial point, and a lot of people say that testable code is essentially synonymous with good code. Well-designed code is testable, and shoddy code is not testable. So that's one view. That's one way to look at it. The other is that testing provides comfort, as I said before, for you, for your coworkers, for future developers on a project. But tests can serve a lot of roles. They can be a way to further your design. They can be an indication where issues exist. So, as an example, you have a test suite. So, hypothetical test suite, abstract idea. You have something, we'll call it a test suite, that you can run against your code, and it's going to say, hey, there's an error right over here. That's not something that you have without tests. You can't look at your code and be like, oh, no, that line right there, these two numbers, they're backwards. Okay, let's call this a day. Can I get my paycheck? But tests can also serve as requirements. We'll see this a little later when we look at small test suite. You can look at what's being tested and say that, again, under the assumption that this is tested code to the fullest extent possible, you can say, well, these three things are being tested, so these are the three things that need to be true about this piece of software. And against regressions, moving backwards is not really the direction that a lot of people strive for. So while you're making changes to your software, tests serve as a way to, again, show you the same way it shows you what's breaking. It can show you what you're not keeping up to date. As you make changes to a piece of code, the tests will break over time, and maintenance to tests is one of the things that we'll talk about in the next slide. It's a trade-off, but it does give you a guard against regressions. You can iterate quickly. And this is something that there's a lot of hype, we'll call it, around agile software development and continuous delivery, continuous deployment. Those, I won't say meaningless words, but those very fluffy words that people like to say. The idea of all those things, regardless of which label you want to give it, is fast iteration. You want to iterate quickly and make changes, add new features. You can't do that unless you are sure that what you've built in the past continues to work, or else you're just swapping in features for other features. But as with everything, it's not a free lunch. So tests are their work, obviously, right? They're not going to write themselves. You're going to have to write tests. And there's certainly a number of trade-offs that come with tests. So, first and foremost, bad tests are better than no tests. So this is one of those situations where people say, well, okay software is better than no software. And that may be true. That may not be true. But tests specifically is one of those things that bad tests are not better than no tests. They provide false comfort, and they can misdirect efforts when you're trying to fix bugs, general maintenance. And maintenance of the test as well is another trade-off. You have to, as you want to get regression, if you want to guard against regressions, you'll need to maintain the test as you maintain your software. And unfortunately, or fortunately, depending on how you look at it, you will write a lot more test code than production code. So what are we talking about here? We're talking about, say, 2x minimally. You're going to write twice as much test code as you wrote to actually write the piece of software. And that sounds crazy. You're thinking, well, why would I want to write software and then write more software to test that software? That sounds like extra work, a lot more work than there went into the original product. And the fancy word, it's not a buzzword, but it's a fancy word. It's called cyclomatic complexity. And really what that means is you're going to have very, very simple test code. You're going to have a lot of it, but it's going to be very, very simple, dead simple. And we'll see a bit of it in a demo. But the test code that you write will be very simple compared to your production code. And at the end of the day, it will always be up to you to really choose whether or not you want to test your code. But I can say that if you don't, your prof will, your users will, and bugs in your code hopefully don't lead to anything drastic, but that depends a lot on what you're building. So that's the what and the why. What is testing? Why you might be interested in it. But how? How do you do this abstract thing called testing? It sounds really fancy. There's a lot of big words to surround it. How do we actually go about testing our software? So this, right? One of my pet peeves with testing in general is that a lot of the quote-unquote literature is almost what's the word? Patronizing, in a sense. When you read up on testing, it's always, well, here's an add function. You have X and you have Y, and then if you add those two numbers together, yeah, you have a function, and then you can test that. You have a test add. You assert that add 1 and 2 gives you 3. We're all experts here, right? So that's it. That's it, folks. Really, that is nothing like what we write on a daily basis. So one weird trick that you can use to, I apologize for the slide title, but one weird trick to testing your code is just make everything look like this. While it is actually simple in appearance, you can essentially write your code in such a granular level that each part of your code, each component, each function ends up looking something like that. Granted, obviously, no web application today, no command line application, no desktop application is a collection of add functions. But certainly, you can think of the smallest pieces of code that would make up your application and reduce them down to something that looks like this. And so what's nice about this? Namely, you have arguments coming in, and you're returning a value. There are no quote unquote side effects, right? There's nothing fancy going on here. You're given inputs, and you return output, and And that's really the trick to testing a lot of things. So yeah, I guess really you look at this and you think to yourself, when was the last time I wrote something that simple? That's a silly example because I write nothing that looks like that on a day-to-day basis. But you can reword that question to, when was the last time I wrote something that testable? This is super testable code for a reason. So it's not easy, right? But there's a process to it, and there's a process I follow. Obviously, it's not the process that everybody follows. But when I look at a piece of code that I have, I ask myself, what do I want to test? What portions of this application, this function, this whatever, is worth verifying? And the answer is not everything, right? I think the naive, in a sense, approach to this would be to say, well, if I got to test it, I got to test it. I got to test everything, every line of code in this program needs to be tested. Some people will talk about 100% test coverage. That's not the end goal. You don't want to strain yourself to try to test everything because it's not worth it. This is another one of those times where the 80-20 rule applies. 80% test coverage is, well, no. Some sort of 80-20 rule applies here. Take it as read. So when you are going about testing your software, when you're writing tests, one of the things that you can strive to do is something that I think it stems from the medicine, the field of medicine, but it's applicable to a number of things. It's something called differential diagnosis, and what that breaks down to is testing things in such a way that each test gives you some new piece of information that you previously didn't have about your software, right? You always want to ask yourself, in addition to what do I want to test, when you are going to go and test a piece of software or a portion of your software, what does this test passing tell me, and what does this test failing tell me? All right, so demos. Snap. All right. So I have here some files, a few example files. What we're going to do is we have all right, so we have, oh gosh, in a database somewhere. So you can imagine a scenario where you have some really random requirements, but the actual situation that we're writing this in really doesn't make a difference. What I want to talk about is kind of the approach to testing and how it looks. So you have some table with data in it. I pulled this off of the open data website for the province of Newfoundland. It's weather stations in the province, I guess. But you can see here that there's a station ID. There is a latitude, longitude, there's an English name, and I guess a station type, right? So we can go over here. Hopefully the internet will be kind to me. Let's look at tabular data sets. So as you can see, this is the open data site, but brand spanking new, only from the 3rd of this month. We have weather station climate monitoring data, so we can go here. If you want to take a look at this data yourself, this is station information. So this is that table here. So you can imagine a scenario, hypothetically, that you have a database somewhere and you have some values in it, and you get tasked with, so you have some site, for example, that say you have someone that's built a site and they give you the site and you have that data somewhere, and you're tasked with writing a script to pull data from that database and show it on this site, for example. So this site takes, as you can read in the top right, a zipped shapefile, and you can click add file and so on and so forth. So really, I guess, what's the process for something like this? You need to connect to the database. You need to read in values, parse them, maybe, write them out to a shapefile, upload them to the site. What portions of that are we going to write a program for? So specifically, we'll write something that takes this data, writes it to a shapefile. We can manually upload the file afterwards. It's not a huge deal. So what we can do, we have a script. So let's do. So it's Python. We have a script that, and again, most of this is boilerplate. But what we want to do is pull data from this table. So let's walk through the process for that. We need to connect to the database, figure out what portions of the data we want to read, and so let's take a look at the schema, actually. So this is the schema for the table. What we'll notice is that longitude and latitude are strings, right? So what you would normally represent as in double or float, or whatever in your particular language, these are strings. So what we need to do first and foremost, if we want to display this on a site, is we'll need to, because everything else we can take is read. The value here, that's not important. So what we'll do is take this and we'll take the name and we'll write that to a file. But we need to parse this from this notation into a double, for example. So what sounds relatively straightforward, but we want to test this. So how do we do something like that, and how do we test it? All right, so let's the best version control is adding numbers to the end of files. So what we can do is in Python, there's something called, so if you're not familiar with Python, import brings in basically everything and anything under the sun. I imagine you've all seen the XKCD where you import anti-gravity, but I digress. So we are going to import something called unit test. And a bit of boilerplate, but we'll write a class called test. test create shapefile. Extends from unit test case. So this is what boilerplate test code looks like in Python. It's nothing crazy. But the notation that we saw previously, this notation is degrees, minutes, seconds, and then we have a direction, and we have that for latitude, and we have that for longitude. All right, so right now, what we have is a script, and we can pretend, for example, that our coworker wrote this script. So we have Python, create shapefile. We can give it a config, actually. So let's take a look at the config first. So we can imagine we come up with this. We want to essentially run this query against the table, pull out that data, take its X and its Y, map that to a point, add two fields to it, display that as a shapefile on our lovely site here. So the first thing we're going to need to do is execute that query. And then we're going to have to map those values, assuming that it's expecting a latitude and longitude to be represented as decimal degrees. We're going to have to map those values to their decimal degree counterpart. So we have script Python, create shapefile, and we pass in that config. For those of you who are familiar with the ArcGIS suite, there's a good joke. You know that Java joke where they talk about knock knock who's there, and then you wait a couple seconds and you say Java. Because we're all really great comedians in computer science. There's a variation on that we switch in Java with ArcPy, and it's a riot in ArcGIS circles. But so we have some script that takes care of all the rest of it. What we're left with is parsing those field latitude and longitude into their decimal degree counterparts. So what we want to do is we want to start with test. So we have test create 2, again, good version control, habits. So we have something here. Actually, So you're making some change to a piece of software, and you have to write a function that takes in a string value and converts it back to its float counterpart. So we want to go about testing this. How do we write a test for this kind of thing? Well, back in this file, we can import essentially what testing looks like is you have some code that does something, and you write something like this, another class, another file, another component, whether it varies from language to language, but you write something else, and you call that portion, right? At the unit level, we consider it to be functions or what have you, but you call some portion of it, and you verify its output. So we know that we need to write a function that converts a string to decimal degrees, short for D, or DD short being the short form. So we're going to pass in a string value here. And conveniently, I have actually, let's just copy and paste something from here. So as an example, oh no. Let's take that. All right, so we have that, and what we can do, self dot assert that the decimal degrees that we return back from that function are 47.1. As an example. So we know that there returns the decimal degree version of that. So what does this look like when we run this? As an example. So I say Python test create shape. And so we run it and we get an error, right? So we have, of course, Python being Python. Right, so we get this back. We say, okay, this makes some sense to us. We have a function that takes in no arguments, but we're passing it in a string, so that makes more sense. So in our implementation, we have hard-coded 0. So what we're saying right now is that for every string value that you can give me, you're going to get back a string value, or you're going to get back 0. But that's not true. All right. So what we want to say is, so we know that has the first two portions of that, for example, are the decimal degrees. So we can say turn instead of 0, we say DMS :2. Right, and in Python, that's just giving you the up to two characters of the string. Right, so we get it back and we say, because types. We have string 47 is not equal to 47, the integer 47. So in here, what we're going to do, there we go. Right, so what did we just do? We had a bit of code that we wanted to write, a change that we needed to make to a piece of software, and we've heard about this testing thing. Sounds interesting. There's a lot of people talking about it, and we wanted to try it. So what we did was made the change, wrote a test for it, and what we have now is a piece of code or a command essentially that we can run that gives us back whether or not that piece of code is working. Right. So this is all those things in just a couple lines. Right. This is all those things that I was talking about before. This is a guard against regressions. So if I change this to 4, right? So we get a lot of functionality out of something extremely simple, right? It sounds fancy, but realistically, that's the process that you go through to test a lot of software. You break it down into something relatively simple, relatively benign, and test that functionality. So let's go back to our test. Right, but we know that this is actually supposed to be some other value. This is actually supposed to be 47.7, and I just did the math real quick in Python. So we have this correction. This correction came back and said, well, you're giving me 47. Realistically, 47.7 is what we are expecting to get back. Let's go back to the previous implementation that we had. With this new test, it's still not the same. So we have a requirement here. We have in code, the best place to have it, we can version control it, etc. We have the explicit statement that this string representation of degrees, minutes, seconds is actually supposed to be parsed into this particular value, right? And you can imagine the same thing for anything. You can say, this is parsing a string, but say there was some relatively complex algorithm that you had to perform, and you get back a value. You can essentially enumerate a number of steps that say, this is the expected output for this input. All right, so let's cut that off. So let's fix this up. And here we're going to have to actually implement the conversion correctly, because there's no particular subset of that string that returns you that or has that value in it, so you can't just parse that out of the file. So the math behind this is decimal degrees is equal to, if you have a string, for example, that's 47 degrees, say 52 minutes, 55 seconds, as an example, it's this portion with that, and the initial portion is the degrees, the minutes you divide by 60, and the seconds you divide by 3600. So we can do, say, DMS. Run the test. That's obviously not parsing correctly. So this is the for times. So I'll paste in the end result, but we can see that all right, so we get this back, and fractional. What we can do is init, just going to check to 7. As an example. But actually, better yet, we know that we don't need all these decimal points, because 5 decimal points generally is a meter's accuracy. Don't hold me to that. But after 5 decimal points, we no longer really care about that's being that specific. So we can run that. And those two things in software aren't actually equal. But what we can do is, and you'll see something similar to this for a lot of testing frameworks, is the idea of different types of assertions. So you might not want to test that 2 things are equal, but instead that they're almost equal. Right? And you can specify a delta. Let's go 10 plus 5. So there we go. And we're back to understanding what state the software is in. We know that we can give it this input and get back that output, right? So we can run config, and this should work now because we've implemented that function that was missing. So we have in our working directory, shapefiles is not a single file, because why not? So we can zip these up into a foo.zip. So we have a foo.zip, and we're a zip file. So what we can do is over here, we can add file, foo.zip, and we see it on the map. Right? So you can imagine some process similar to this for every other function that you write. So next function you might add is something to instead pull another column value, for example. All right. So one of the things that you'll quickly run into is that you're going to rely on third-party software. So you're going to have to be like, oh, okay, well, I need this database driver to pull in another column. I'll need a database driver, and I'll need to set up a database. And what we'll get to in time is buzzwords. So as you start to delve further and further into this this field, or this I guess whatever you want to call it, this activity, there's a lot of buzzwords, as with a lot of things in computer science. So you'll hear things like TDD, acceptance testing, mocks, stubs, fakes, test doubles, all these things. And it's overwhelming. Realistically, this is why nobody likes talking to computer science people, because we throw in words that we think have meaning, but realistically they don't. So what do these words mean? TDD, as an example, is the process that we just went through. We just did TDD, and we just wrote a test before we wrote the implementation. We have fancy words for that, right? Things like that. that is one of the larger barriers to testing is the words that you'll run into. These are all hyperlinked with relatively sane explanations of these words, if you're so inclined. So really, what am I asking you to do? So I think in marketing speak, this is a call to action, but realistically, just test the next thing that you write. You're going to write some addition to this current piece of software you're working on. You're going to start something fresh, which is the best way to go about it, because greenfield development is obviously the only development that should be done. Every new application should be written from scratch, from the ground up, because why not? But you'll pull in something called a test framework, which is what we did with Python. Python has batteries included, so we imported a unit test at the top of the file. But in different languages, you'll bring in whatever. So JavaScript, you have tape, XUnit, JUnit, unit test that we did in Python. A quick Google search will bring you to a list, an endless list of whatever frameworks there exist in your language of choice. The important thing to know is that they are all the same. Despite what anybody tells you, they all do exactly the same thing, and there is really no difference in choosing one versus the other. It's worse in JavaScript than any other language, but that's a different rant. But people like making frameworks. People like testing, apparently, so they make a lot of test frameworks. It's good for us because we have choice, but we don't want to get stuck on choosing. Just pick the first one alphabetically in the Google search. Take that, use it. The most important thing is the actual activity of testing, the actual activity of thinking about what you're expecting to do and what you're expecting to happen. So write a test for the next thing you do. So the slides are online. There's resources here, resources that can explain the process a lot better than I can in 40 minutes. And that's all I got.